Well, I'm taking a little break from my physics and astronomy video sequence to show you a verification of the formula for the area of a triangle, 1/2 base times height. And the history on this for me would be that in 1966 I went to the University of Iowa for a summer school program for high school students and learned to program in FORTRAN, and also took a math class. But one of the first programs we wrote in FORTRAN was to calculate the area of a triangle. Of course, we used 1/2 times the base times the height. And I'd like to show you some verifications, not quite proofs, but some verifications that this formula is correct for some different cases. The first case being a right triangle. So I've drawn a right triangle here, and then I've completed a rectangle. And the right triangle, labeled same, has the same area as the crosshatched right triangle. They're completely similar triangles. They're just flip, and you would have the same H here, same B here, same hypotenuse. So it's equivalent. I am assuming that we can use the area for a rectangle of base times height. Base times height. Then we have two of these triangles, and let's write it as two areas, each area being 1/2 base times height. There we are. The area of one triangle is 1/2 base times height. If we have two of them, 2 times 1/2, those 2's cancel, and we have the area of the rectangle, base times height. So let's try a different type of triangle, an acute triangle, where all the angles are less than 90 degrees. And we have here, again, I'm going to make use of what we just developed here. But we have this acute triangle and cross-shading two right triangles inside this acute triangle. Each of these has its own rectangle, and again, the cross-hatched area here is the same as the area up here. The cross-hatched area here, the triangle or the rectangle that it is part of, we've got the same area in that white space. So the two areas would be 1/2 base 1 times height plus 1/2 base 2 times height. So we have a B1 and a B2 for the two separate rectangles. Those are the bases. We can factor out 1/2 and h. That's common to both terms. So in doing that, 1/2 base, we have 1/2, h, and then B1 plus B2. Well, B1 plus B2 is the base of this acute triangle. And we recover now 1/2 HB, just swap B and H, 1/2 base times height. It works for an acute triangle. What about an obtuse triangle? I'm going to do a couple of different cases here, but let's take this side to be the base first. I'm going to use a different side to be the base in the next little part that will be revealed. But here I'm making a right triangle by adding in this shaded area with base x and height h, that triangle. And we have our original base b that goes from here to here. It also has height h. So this large triangle is now our case 1 situation again. It's a right triangle. It's fitting in this rectangle, and it'd be 1/2. The base is x plus b, and then times the height. That's the area of a triangle, and we're doing this full large triangle. What about the triangle area that's in this red shaded area? Well, that's 1/2 x times h. That's the base. So to get the area we need, we take this full area, 1/2 x plus b times h. That's the large right triangle. And we subtract the area of this small right triangle. That will leave us with the cross-hatched black area. And just expanding this out, 1/2 times x times h, that's a term. 1/2 times b times h, that's a term. And we've got minus 1/2 xh here. So the 1/2 xh minus 1/2 xh is 0. And we're just left with 1/2 base times height, as we should be. The area of the triangle has been verified. 1/2 base times height. That works for an obtuse triangle. But you may be curious, I selected this side to be the base. What if some other side was the base? Well, let's try that. And here, it's the same triangle. I tried to draw it as best I could to be the same triangle. But now we're going to choose a base here. And there'll be some different swapping around of letters here. But let's first go with base B here and x at this point. And I'm going to just scribble this off for a minute so it doesn't get too confusing. So we have base B here. I'm going to take this as the base. Another right triangle with a base x here. And then h gets us the height of the triangle. H is perpendicular to the base direction. So h is over on this side. So we have a rectangle again. B plus x is one side, h is the other side. That's our starting area. And now this large triangle, if we take a look here, I can do 1/2 b plus x times h. That's the section right here. That's half of the rectangle. Again, sort of following along with case 1 that we studied. What about the obtuse triangle area? How could we represent that? Well, if I take the large right triangle and now subtract this red cross-hatched area, I'll be left with the area I want. So 1/2 b plus x times h, that's the full large right triangle, minus 1/2 x times h. There's our right triangle here with base x and height h. Again, distribute through here, so 1/2 b times h, that's a term. 1/2 x times h, that's a term. And again, we have this cancellation. The 1/2 x h terms add to 0. And we found that the triangle area is 1/2 b times h. Now, b and h are different. The exact symbols are different numbers in these two examples. Base b here is a longer distance than base b here. But the numbers work out and we get our same result. What about using calculus? So if you need to stop at that point, if the areas are enough, that's fine. But let's use calculus and determine the area of a triangle. So I have xy coordinate system here. I have a straight line, y equals mx plus b is the equation for a straight line. And this b is y-intercept. This is not the base. But I've drawn this such that the line goes through 0 at the x and y origin. So that makes the y-intercept 0. So this line has the equation y equals mx. At the case that x is equal to b, the height, that's our y value, the height would be calculated by h equals m times b. This b is the base. And m is the slope of this line. Well, let's so that's our h value. We'll see how we'll get back to this in just a minute. Let's calculate the area using calculus. We want the area underneath the curve. Curve here is a straight line. Curve is a general term. But to find the area underneath a line or a curve, we do this antiderivative process. So we're going to start summing the area, starting with the area at 0 and ending the area at b. So our function that we're taking the antiderivative of is mx. Y equals mx. And our notation for the antiderivative, we then have dx as our infinitesimal. And we're going from 0 to b, starting and ending limits. The m is a constant. I can pull that in front of the antiderivative. X is to the first power. And when I have a function x to the first power and then dx, to process this antiderivative generates one higher power, and then you divide by that new power. So 1 higher than 1, that's a 2, and we divide by that 2. Then we must evaluate this x squared over 2 at the beginning and ending limits, the lower and the upper limits. So we're going to evaluate at 0 and b. First we evaluate at the upper limit, b. We replace x with b. We still have the m out in front. When x is replaced with b, we get b squared over 2. And then I subtract the evaluation of this with the lower limit replacing x. Then, of course, 0 squared is a 0. So this term is 0. So our area is m times b squared divided by 2. That's not quite 1/2 base times height, but let's see if we can manipulate a little bit. Well, this area, 1/2 mb squared, let's factor off a b, and write b squared as b times b. So 1/2 mb, and now I'm going to move one of these b's out in front. So 1/2 b, and then mb. Well, what is mb? mb is h. It's the height. So I replace it, and we find the area of a triangle using calculus is 1/2 base times height. 1/2 base times height in every situation. You could do a third situation over here, choosing a different side to be the base, but you'd come up with the same result. You might want to do that just to verify that you can work with areas. The area of the triangle, 1/2 base times height.